So this is the second problem in switch chart series. So here a 100 plus J 150 ohm load is connected to a 75 ohm characteristic impedance lossless transmission line. Then find the value of the following: reflection coefficient, VSWR, load impedance, the input impedance, Vmax and Vmin location. Right. So in the previous problem, we have seen how to calculate reflection coefficient, VSWR and the input impedance. Those people who have not seen the earlier video, kindly see that so that this problem is also familiar to you. Right, anyway, so what is the first step in this kind of switcher problem? You need to find out what? Yes, you need to find out the normalized load impedance. Yes. So what is normalized load impedance? Small zr equal to capital zr divided by capital zr. So here, so capital zr is 100 plus j150 and capital Z0 is 75. So 100 plus j150 divided by 75. So 100 by 75 is 1.33. So 1.33, 150 by 75 is 2. So 1.33 plus j2. Now we need to plot the point small zeta in the switch chart. Yes. And we also know that how to find the reflection coefficient value, right? Quickly, I'll go through it anyway. So in order to find a reflection coefficient, 1.33 plus J2, this point should be plotted in the switch chart, right? So now, where the value 1.33, right? So here the value is 1.2, here the value is 1.2. This is 1.3 and this is 1.33, right? So this value is 1.33, right? So what about J2? So this is 1.33 and here plus 2. Plus 2 means you have to look at the above the real axis 0.4, 0.5, 0.6, 0.7. No, this is the plus 2, right? So this is what the small zr value, right? So now after this, what you'll do usually? Yes, it will do. Here you'll be marking this is your center point, right? So for finding reflection coefficient, it will do from this from here to here. Yes, correct. It will do from here to here. You will be making an arc, right? So this length you have to make an arc to where? This arc you have to interpolate to here, right? So when you are making an arc here, so it will be exactly cutting over here, right? So now we can see that the reflection coefficient magnitude is around between zero point 0.6 and zero point 0.7. So let me consider this point, mm, sorry, not zero point 0.4, zero point 0.3, zero point 0.4, zero point 0.5 and zero point 0.6. Between zero point 0.6 to zero point 0.7 is the magnitude of reflection coefficient. Similarly, we need to find out the angle. For angle, what you'll do? Yes, correct. What you'll do? You try to extend this out, extend it to the outer side of the switch chart. Then you have to look at the angular reflection coefficient scale. The value is 0, 10, 20, 30, 40, like this, right? So here the angle is 40 degree. So from this we can understood that the reflection coefficient magnitude is 0.65. The angle is what? 40 degree, right? So now we found the reflection coefficient. Next what you'll do? You need to find out the VSWR value. How do you find out VSWR value? Yes, you need to tell. And what you'll do? Yes, for that you have to draw a circle, right? So here we'll be drawing a circle, right? So this circle is known to be what? This circle is known to be named as VSWR circle. So now I call it as this is VSWR circle, right? So next, if you want to find out VSWR circle, what you'll do? You try to find out where it is intersects at the real axis. So here the value is around 4.825. So I can call it as VSWR value is 4.8, or I can call it as VSWR value is 5, right? So for finding VSWR, you have to look at the VSWR circle where it cuts the right hand side of the real axis. That is nothing but the VSWR value, right? So these things we found, right? So what about the next one? What we need to find next? We have to find out, it is second, right? So we have to find out the load admittance, right? So that is also very easy, the load admittance. What do you mean by impedance? Load impedance? Yes, this is the small zr is load impedance. For finding admittance, what you will do? See, we know that the impedance small z, impedance is always reciprocal to admittance. So in the same way, in switch chart, this is small zr, right? So what you have to do is that for finding impedance, sorry, admittance, what you have to do is that here you need to extend the zr line opposite to opposite end, right? So we have, it is intersecting with yr, right? So this is the point where the where the straight line is intersecting, right? So this value is nothing but yr, right? So now we need to find out the value of yr. For finding the value of yr, you need to trace. Don't trace. I mean, don't take the value. You need to trace like this, right? So this is 0.3, and here the value is like this, right? So like this, we have to trace, right? So now what is the value of yr? The real value is what? 0.2. So 0.2 to 0.3. So the value is 0.22. What about here? The imaginary value is 0.3. So yr value is going to be what? 0.2 j 0.3. Whether I have to put plus or minus? Yes, we have to put minus. So zero point 0.2 minus j 0.3. 0.22 minus j 0.3. This is nothing but the normalized load admittance, right? So when you want to find out the, this is normalized load admittance, right? So if you want to find out the original load admittance, what you have to do is that we know that, right? So what is the formula we can use it? YR, that is small yr equal to, we know already, capital YR divided by capital Y naught, right? So what is 1 by Y naught? The reciprocal of characteristic admittance is YR into Z naught. So small YR equal to capital YR into Z naught. So finding capital YR, what will do? Small YR divided by Z naught. So what is small YR? Just now we found out, right? So what is small YR? What is that? Yes, what is this value? 0.22 minus j 0.3, right? So 0.22 minus j 0.3. What about z naught? Thus we know that is 75. So when you are dividing this value by this value, you will be getting the value of load admittance. This is how we have to find out the load admittance value, right? I hope you are clear with this, right? Yes. So then we are going to find out the next parameter, that is input impedance at 0.4 lambda from the load. This is very easy, right? We have seen this. ZS at zero point 0.4 lambda from the load. In the earlier problem, they are giving the frequency specification and velocity specification. From that, you are finding the value of lambda. That is 1 lambda equal to 90 meter. After finding lambda, you are comparing that lambda with the length of the transmission line. And you are converting the length of the transmission line is also in terms of lambda, right? But here there is no need to do that because already the length of the line is given in terms of lambda. So just you need to trace it. From the load, you need to travel zero point 0.4 lambda towards generator, right? For that, what you have to do is that, see, look at this is your switch chart. So this is where your wavelength towards generator. Already I told you, always you have to look at wavelength towards generator scale because already we are at the load, right? We need to move towards source or we need to move towards generator. That's why I am taking the outermost scale. I am not taking the wavelength towards load scale. I am taking wavelength towards generator scale. Please remember, right? So in this we know that this is 0 lambda, and what about this? This is 0.25, and what about this 0.25 lambda? Again, if this is coming here, this is 0.5 lambda, right? Okay, fine. So now already where we are? We are at the wavelength 0.19. What is that value? 0.19. Yes, 0.19, 0.2. So can I assume 0.194 lambda? Yes, yes, obvious. 0.194 lambda. We are at 0.194 lambda. From this, how many lambdas we need to travel? Yes, 0.4 lambda. For that, what you have to do? From this 0.194 lambda, you have to add the value 0.4. So what is 0.194 lambda plus 0.4? 0.594 lambda. Where the value 0.594 lambda? Any idea? Yes, already this is your 0 lambda, right? So this is your 0 lambda and this is your 0.25 lambda. Again, if you are coming back, this is 0.5. Next, if you are traveling here, again it will go to 0.5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 5, 7, 5, 8, 5, 9.6. So like that here 0.75. Again another in 1 lambda, right? So like the value will be rotating, right? So now we need to note down the point 0.594 lambda, right? We have to note down the 0.594 lambda, right? So we know that this is 0.5 lambda. Let me zoom it in. So this is 0.25 and this is 0.5. So the next value is what? 0. This is 0.51. This is 0.52, right? So this is 53, 54, right? So 55, 56, 57, 58, 59. 594 means 59 2 points, right? So this is your the point 594 lambda, right? So from this, what you'll do usually, from this point towards center, you have to draw a straight line. At some point, this will cut at the VSWR circle. This value is known to be, yes, small. Yes, what is this value? This value could be what? Small ejector, right? So this value could be small ejectors, not ejector. So now if you want to find out the small ejectors, what you'll do? Yes, it will do. You try to trace the value of small ejectors, right? So you try to trace the value in the real axis like this. Okay, so you'll be tracing. You have to trace the value like this. So okay, so I'm tracing like this, and in the for imaginary also we are tracing like this. So anyone, can you tell me what is the value? So the real value is somewhere around zero point 0.3 and the imaginary value is 0.60. So what is small ejectors value? Yes, small ejectors value is what? Yes, from here itself we can update, right? So what is small ejectors value? 0.3 and the imaginary value is j 0.6 plus or minus plus. Why? Because it is above the real axis. 0.3 plus j 0.6. If you want to find out capital letters, what you'll do? Small letters has to be multiplied with capital letter, right? So like that, you have to find out the capital letters. Yes, I hope the problem is clear, right? And now come to the fifth part, sorry, sixth part. Then we'll go to the fifth part, right? So this is also same. Ejectors at the generator when the line is zero point 0.6 lambda long. What do you mean by that? If the length of the line is 0.6 lambda, what should be the input impedance? Right? For that, what you'll do? Already we have traveled how many times? See, from here to here, how many times I have traveled, right? So let me mark it with some value, right? 4 lambda, right? From here to here. And same way, from here to 0.194 lambda, you need to travel how much? 0.6 lambda. For that, what you'll do? Very easy, right? So I hope we are clear. 0.194 lambda plus zero point 0.6. What is 0.194 lambda plus zero point 0.6? Point, yes, 0.794 lambda. Is there any guesses where the value 0.794 lambda is? Yes, obvious, right? 0.794 lambda is, already we know that this is 0 lambda, this is 0.25, and this is 0.5. Again, if you are making one revolution, again this will become point, yes, 0.75. Here, this value is what? 0.76, 0.77, 0.78, 0.78, 0.794 lambda is this one, right? So from this, what will do usually? From this, you will be drawing a straight line, and at some point the VSWR circle is intersecting, right? So this value could be your, obvious, yes, this values could be your small ejectors, right? So now what you'll do for finding the value, what you'll do? You'll be tracing. See, guys, trace the value. Don't look at the line values. So always try to trace the values like this. Okay. So I know the procedure. I mean, I'm thinking that all peoples are knowing the procedure of tracing, right? So this is what the small HTS value, right? So here the small HTS is in somewhere around between 1.8, the real value, and the imaginary value is 2.2, right? So maybe like 1.8, imaginary value is J 2.2. Since it is below the x-axis, and real axis, that is minus. So 1.8 minus j 2.2 is small letters. For finding capital letters, what you'll do? Small letters has to be multiplied by eta. That's it, right? So this is how you have to find out the input impedance when the line is zero point 0.6 lambda from the load, right? So let me mark it down this, right? Yes, right. So up to here, the value is what? 0.6 lambda. You have to note it like this. Okay, anywhere on the line, you have to denote like 0.6 lambda, right? That's it. Right. So what is the next case? That is the locations of Vmax and Vmin when the line is 0.6 lambda long, right? So for that, here for instrument chart, always this is r equal to 0 and this is r equal to infinity, right? Resistance value is infinity, here resistance value is 0, right? So if the resistance is 0, what about the voltage, I mean impedance? Is it equal to 0? Here r equal to infinity means z is also infinity. If z equal to 0, what happens to voltage? Obviously voltage is 0, so can I say the voltage is minimum? Similarly, z is equal to maximum. In that case, can I say the voltage is maximum? So the locations of V min and V max is the left and rightmost part of your switch chart, right? So this is the case, right? If you are considering switch chart as Z chart, then this is going to be the V min and V max location. If the peoples are asking the locations of I max and I min, this could be the maximum current because Z equal to 0, so the maximum current will come. Here, the minimum current will come. The people won't ask. Anyway, if they are asking, you need to remember this is I max and I min. But here, our case will be V max and V min, right? So we need to find out the location, right? So now, please tell me, guys, in this problem, they are asking the locations of V max and V min when the line is 0.6 lambda long, right? So that means what do you mean by that? Yes. See here from this point, this green color, right? From this point, for for reaching zero point 0.6 lambda, how many times we are crossing V max and how many times we are crossing V min? Any guesses? How many times this green line is touch under V max and how many times this green line touch under V max? V min. Yes, obviously two times it crosses V max and one time it crosses V min. So now we need to find out what is the locations of Vmax and Vmin. That is very easy, right? So now the load point is here. Where the load point? 0.194 lambda. What is the value at here? The first time, what is the value here? 0.25 lambda, right? So here the value is 0.25 lambda. Here the value is 0.194 lambda. What could be the distance between these two? Here the value is 0.194. Here the value is zero point 0.2. What could be the difference between these two? That is nothing but, so let me do it here. So that is nothing but 0.194 lambda, that is 0.25 lambda. You have to take the difference, right? So what is the value? 0.006 lambda, right? So 0. And this is 0.056 lambda, sorry, 0.056 lambda. That is the distance between these two. So can I say from the load, if you want to reach the maximum from the load, if you want to travel from the load, if you want to travel zero point 0.6 lambda from the load, if we want to travel zero point 0.6 lambda, we need to cross 2 Vmax and 1 Vmin. So what is the location of the first Vmax? What is the location of first Vmax? That is 0.056 lambda. What about the second Vmax location? Any idea? See, this is 0.056. If you want to retain, if you have to come again the same point, Vmax, whatever the value is there, 0.056 lambda, just add it by which value? 0.5 lambda. That's it. So what is the value? 0.556 lambda. Right? So this is the second Vmax. What about Vmin? Any idea? What about Vmin? Any guesses? What about Vmin? So Vmin, the location is already from here to here. The value is 0.056 lambda. From this, if you want to reach the minimum position, how many lambda we need to travel? One semicircle. One semicircle equal to how many lambda? Yes. What is that? 0.25, right? So 0.25. So what is the value here? Already we are having what? 0.056 lambda. From this value, you have to add it by 0.25 lambda. What is the value? 0.306 lambda. This is the locations of Vmin. Only one location, right? What about first Vmax? First Vmax, the location is 0.056 lambda. How do you get that? We are at the 0.194 lambda and the max is 0.25 lambda. We need to subtract it, right? And how do you get the second Vmax? And whatever the value is the 0.056 lambda, this value you are adding with which one? 0.5 lambda, so that we are getting 0.556 lambda, right? For finding V mean, whatever the value 0.056 lambda is there, that value should be added with 0.25 lambda, right? So this is how you need to find out the locations of V min and V max, right? I hope this problem is clear, guys. Kindly go through each and every steps. Don't skip anything in between, right? If you're skipping this, then definitely the concepts won't be clear for you. Okay, so thank you, guys. We'll see